Hi and welcome back to my class. My name is Swati and I am back again with another lecture of your D and F block elements. Right, so if we talk about the next class, we started with your D and F block elements. We started with the fact that how they are considered to be a transition elements. We talked about the configurations, of course, and I said, and I hope that you would have practiced them, because without that we cannot move further in our chapter. Right, if I talk in the end, if till the point that I remember, I left you with the trends. I started up with your atomic radii and the ionic radii, and we talked about it, and we said that how on moving down the group, every time this is happening, whenever we are moving down the group, because the nuclear charge that we are holding up in between, that remains the same, and somewhere the addition of a new shell, that is happening. And whenever there would be addition of a new shell, the size would increase, of course, that we have done. Apart from that, we did that how the variation of size along the period was happening, and into that we talked about how there was a little exception in the sense when I talked about your chromium and I talked about your copper, right? And why was that happening? Since we have discussed that already, that whenever there is the point of a stable configuration, and that was happening, either it was half filled or it was completely filled, right? That's how it was taking place. Now coming up to the next point, the next property that we have to discuss is your metallic character. So write down the second one. Now if I talk about particularly my D and F block elements, which are my transition elements, what do I see? It is observed that all the elements which come under the category of my D block and my F block, they are considered to be metallic in nature, right? Metallic in this sense, like what do I refer to when I say metallic? If I am saying they are metallic in nature, that means that they have a tendency to give away the electron, right? Because they have the positivity, they would be existing as your M plus, right? That's what it is happening. The next thing that we observe in the case of your transition elements, that would be that they are malleable. Because they are metallic, as I just said, they are considered to be malleable. They are even found to be ductile and having high conductivity, right? And somewhere that is the reason that we would observe a different variation in the melting and boiling point as well, of course, which we would discuss after this. Apart from that, it is observed that all the elements of a D and F block, they have a tendency to exist as good conductors of electricity. Now, why do I say that they have a tendency to exist as good conductors of electricity or even your heat? Now what happens is, whenever I am talking about the conduction that basically happens, that is based on the presence of electrons, right? Because if I have electron, the movement of electron would take place and the conduction of your energy or whether electricity, that would happen. So that's why, because it is not having just one pair, it has the availability of two pairs. The electron that could be in my D subshell, the electron that could be in my S subshell, right? I have discussed about that, because the general configuration, when I say about my transition elements, I consider it as your N-1 D 0 to 10, sorry 1 to 10, and Ns that fills from your 0 to 2 electrons, right? And if I know that how the configuration is going, if I know the number of electrons that are present, somewhere it is possible that conduction would take place, right? Then after that, it is observed that if I talk in terms of my solid state, then the transition elements, they have a tendency to exist as all the three structures which are available to us. As if it could be your BCC, it could be your FCC, and even your HCP arrangement, right? And how is that possible? Now, of course, if I have to talk about the different structures that are possible, the different ways in which it exists, that would be simply on the basis of my enthalpy, right? We discussed that, we talk about that in our solid state, that different particular elements, how on the basis of their size and the enthalpies, they have the ability to exist into the different forms, right? So now if I write down just note down, if I start with writing the metallic structure, I say they have a metallic character. Now what is the thing that proves it has a metallic character? So simply we will write down. Now the first thing that is observed is, of course, that I already told you, that the value, any particular trend that I would be discussing with you, whether it is my electronegativity, whether it is my enthalpy or even my metallic character, that would lie in between of my S and P block. Why is it so? Because my D block, that exists between my S and P block. Now that is the reason that it happens like that, right? Then talking about this, I say the value, first point that is going to be the same every time. I simply say that lies between S and P block, right? That's what is happening. Then I say, I just told you that they have a metallic luster, right? They have a metallic luster, they are malleable, they are ductile. So of course we have to write all that. I can say the transition elements. Now we are doing this in the form of points. We would do that because into your exam, however it may come, it is easier, as I always say, to remember in the form of points, right? Then I say the transition elements, they are malleable, ductile, and what else did I say? I said that they have a high conductivity, right? And high conductivity, and conductivity as in I am referring to the thermal conductivity, right? That's what is happening. Then talking about the next thing, that I said that they have the ability to exist into a different solid states, right? So I can say they exist in all the different forms. And the different forms, as in my CCP, FCC, HCP, be it anything, totally depending upon where the availability of your atom is, the different types of forms, even they could be given, right? Then if I say that how the trend for your metallic character goes, then it is observed that the metallic character, that goes on increasing as I'm moving down a group. And as such, there is no regular trend that I can say that this is happening, because as I discussed with you, when the entry of the electrons that is taking place in my 4D and 5D, because of my lengthenite contraction, somewhere the increase in size is not that evident. The increase of size is not that much, right? So that's why I can say that it can exist in all the different forms, right? Then if I have to discuss one more point, on the basis of its metallic character, now it gets a tendency to show the covalent bonding as well as the ionic bonding. And talking about the bonds, it is observed that the covalent bond, they are found to be more prevalent, right? So I can write down covalent bonding. I'll simply write because they exhibit covalent bonding. So I say they exhibit covalent bonding, right? That's what is happening. Now whenever I have to discuss about my metallic character, I should know about the different possibilities that I have. I should know that of course all the elements, all the compounds which are present in the series of my transition elements, they are metallic in character, they have a metallic character. Apart from that, they are malleable, ductile, they are good conductors of electricity as well. So if you want, you can write that as well, that they are found to be good conductors of your heat as well as electricity. So all these things that we just discussed, they just prove the fact that how they have the tendency to be electropositive in nature, right? Then talking about the next trend that we have to discuss is your melting point and the boiling point. So I write melting point and boiling point. Now we will see, when I have to discuss about your melting point and your boiling point, there is not going to be any regular trend. Why is it happening? Initially, we would see, of course, the temperature, the value of either your melting point or your boiling point, that is going to increase. But then we see a stage that after a gradual increase, there would be a dip in the graph, which is again further going to increase with a slight decrease in the values. Now, of course, we have the reasoning for each particular one of them, and we will discuss that. First of all, let's draw the graph. Now, if I draw a graph between the value of my melting point or the boiling point, now you know one thing, the trend for both the melting point and the boiling point, that would be same. There is not going to be as such any difference, right? If I take up my temperature on the y-axis, right, and I say the elements on my x-axis, elements as in the transition elements that I am talking about, that I have just written the combined name, right. Now I said that the graph shows a increase, right. Then I say there would be a gradual decrease, again leading to an increase with further decrease like this. Now if I start writing, if I start giving you the names, it is observed that the dip that we have observed refers to your Mn. This would be your chromium going from your scandium, titanium, vanadium, showing a gradual increase. So I can write down, this is my titanium, vanadium, right. Then I observe a dip in my graph, that is related to my Mn, manganese, right. Then again I have an increase, iron, cobalt, nickel, and then simply I see copper and zinc, right. So now if I see, first of all I say that from my scandium till my chromium, I see a regular increase in my graph on the values of my melting point and boiling point. Now if you remember, when I used to talk about the melting point and the boiling point trends into your S block or your P block elements, I used to say a word regarding the van der Waals forces, right. We used to say that, we said that the van der Waals forces, which were directly dependent on your atomic size, as the size increased, the van der Waals forces increase, and that's why the value of your melting and boiling point used to increase. Now, why I am saying that? I am saying that to recall you the fact that this time we are not going to use that. We do not have to give the reasoning, because every time whenever I have to talk about the temperature, I say about the van der Waals forces, but this time we do not have to do that. The only reason that, that is observed, because we are seeing an abrupt graph. We do not have a gradual increase or a decrease. We are seeing just the abrupt changes. And these changes, they are totally responsible on the interaction between your S block and your P block. As I said initially, when I was talking about the size, I gave you the thing, I gave you the fact that initially we observe increase in the size that was happening along a period, decrease in the size along the period. But then after a certain point, there was observed to have an increase. Now why that was happening? Initially it was because the fixed nuclear charge that was there and the addition of new electrons till my chromium. But after that I got a stable half-filled configuration, right? And when I get this stable half-filled configuration comes into play, comes into role the effect of your shielding. And because of that, somewhere, because of my shielding effect or my screening effect, the value was observed to increase again, right? Now the same way I have to say about this thing, I'll say simply from my scandium to my chromium, I'll say because on moving along the period, the size is decreasing somewhere because the interactions are stronger now. The bond which hold the atoms becomes strong, the melting and boiling point that increases, right? But after that, for my Mn, when I say there is a gradual dip, there is a dip in it because of the stable half-filled configuration. And if it is stable, of course, if the configuration is half-filled, it would be easier to have a lower melting point. right? That's why simply the reasoning that I have to give for the dip in my graph, that would be on the basis of my half-filled configuration, right? Then coming back to an increase that I observe, again that would happen because now again the size would start to decrease, but after that I have a decrease. Now that is happening on the basis of your screening or the shielding effect of the s orbitals, which is taking place on your d orbitals, right? So basically what we have done is we have to include your 3 points. First of all, I'll talk about the size decrease, which is happening simply on the basis of electron addition. Then I have to talk about the half-filled configuration, and after that I would discuss the screening effect, right? So when you have to give the trend, whenever you have to give the configuration or the classification, or you have to simply discuss, what you have to do is you have to keep these 3 points in mind, and after that we can give the particular trend, right? So now of course we have done the discussion, so you can note that down, you can write it down on the basis of that. I'll just write the point because of for this particular dip I say stable half filled, right? And then for my zinc I say completely filled, right? Now that is the particular trend that we observe for your melting point and your boiling point, right? Now coming up to the next thing, if I have to discuss about the density. Now what could I say about your density factor? Now I know this thing, that density, that is nothing but my mass upon volume, right? I have been talking about that, I give that formula in general. So if I write simply, I can say rho is equal to m by v. Now when we talk about the trend of your density, the value of density, now it is the only property that is going to observe a gradual increase. That means when I am going from left to right, I go from a scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Now I have said this thing because so that if you will keep on repeating that as well, even you can remember the names and you would be able to write down the periodic table properly, right? So I say that I have my density, that is nothing but my mass upon volume. Now what happens is, I say that the value of density for particularly my D block or my F block or simply my transition elements, that shows an increase. Now the only reasoning that I have to give is, that's why I have written the formula as well, we will say because the density is inversely proportional to the volume, and the volume of the transition elements that is observed to show a decrease. That is happening because, as I said, that's fine, that is totally fine, that when I say I have a half filled configuration, I have a full filled configuration, I have everything. But when it comes to the volume, here I was discussing about the size, good enough, but when it comes to the volume, I need to talk about the quantity. And if I see, I know this thing because of the addition of electrons, because of the addition of something new, the volume is going to increase, right? Because that is not affected by the fact whether my size is what, that doesn't matter. What I have to see is the total area, the total volume that my element that is occupying, right? So I can simply say, if I have to write down the density trend, I'll say the value of density increases how? On moving along a period, right? I say moving along the period. Now for that, I'll say that I've given the fact that the value increases on moving along the period. Why is it increasing? I'll say because there is observed a decrease in the volume. and simply as it is written there, my density that is inversely proportional to my volume. Because my volume is decreasing, because I see a change or observe a decrease in the volume, I can simply say that is going to lead to an increase in my volume, right? So note down this one. Now, of course, on the basis of the volume, you would be able to give the variation that we observe in the case of your density, and that's how you have to give it. Only and only write the concept. That totally depends. Do not mention anything about the size, because size is a quantity, or I'll say, size we generally mention when I have to talk about your melting point or your boiling point. So, every time you have to talk about your density, because volume and size are two different things. That's what we have to discuss. Now coming up to the next thing, I'll say the most favorite property that we generally discuss, and the questions, they generally come from this property as well, nothing but my ionization energy. So write down the next one. The third one that I want to discuss is my ionization energy, right? Now, the first thing that I have to do is, let's just draw the graph first, and then we will discuss how the variation is happening. Now, if I talk about the particular trend for your ionization energy that I observe is that it goes from somewhere like a decrease in the initial, then leading to an increase. Now, scandium, titanium, vanadium. Till my chromium, at the point of my chromium, I will observe a decrease. Then coming up to my Mn, chromium, manganese, and my iron, I'll see an increase. Then cobalt, nickel, copper, and your zinc, they go somewhere like this. So, if I mention the main points that I have written, I am starting from a scandium. This is nothing but my chromium. Then I am observing just an increase. Mn, iron, cobalt. If I say, in the end, it is almost the same. So, I can draw it something like this. So, it goes till my zinc. Alright. Now, this is nothing but my ionization energy versus the transition elements. Now, first of all, if I say like what is my ionization energy, if I have to discuss my ionization energy, I know this thing, the energy which is required to remove the outermost electron, right? Now, this is what my ionization energy refers to, and I know about the electronic configurations that I have. So, somewhere on the basis of the electrons which are available, I can give the comparison, right? If I talk, first of all, we will come on to this one, we will discuss each one of the values. Before that, now this is what I am talking about, your +2 oxidation state. The trend that you would be observing would be totally different if you want to talk about the +3 oxidation state, or if you want to talk about something else, right? Then I say, this is of course my 3D series. If I have to discuss for your 4D series or your 5D series. Now, if I have to talk about the 4D series of the transition elements, the value of ionization energy, that would be almost the same. Almost the same as in the case if I am talking about the trend. And the increase in the value that I would be observing, that would be very less, not as such. I mean, the difference into your 3D and 4D is not much, not as much comparable. But if I talk about the ionization energy of the 5D elements, now what do I see? When I compare it with my 3D series, the value of the 5D is found to be very high. And if you remember, when we used to talk about your p block elements, or when I used to talk about any normal family, let's take up your nitrogen family. When we discussed about that, we used to say moving down the group because the size was increasing, right? And because of which your ionization energy that used to decrease, because I needed very less amount of energy, because the electrons, they used to lie on the outer shells, they used to be on the outside, not much in the interaction of nucleus. So that's why the energy that was required, that was found to decrease and going from the top to bottom. That's what we have discussed, right? Now after that, I come to the point where I say that now I have to discuss for your 3D, 4D and 5D series. But this time I say there is no decrease, there is an increase in the value, right? Now the size is increasing again, I know this thing, that there is no as such different change. But if I talk this time, I am talking about the transition elements, I am talking about the lengthened contraction. That means, because of course the value that should increase, the value is increasing on the basis of the elements, but if I am comparing it between my different series, if I am comparing it between my 3D and 5D, there should be not as much increase as I observe. Now of course for that, if you have to give the reasoning, if you have to write down that particular thing, so you will simply say that ma'am, this is happening because of the lengthened contraction, right? Now that you can say. Now coming back to my 3D series, that's what I have to discuss. Now first of all, I see that there is a decrease in the value, right? Now this is happening, of course I know the thing that when I am moving along a period, my size is decreasing, right? Because into the same shell, the addition of electron is happening, I know this thing. And now I am talking about the d orbitals and the s orbitals, and every time I have to keep in mind somewhere the effect of my screening or shielding, right? So simply when I am going from scandium to a chromium, every time you have to give the reason, you know why I am repeating almost the same thing. You would see that into all my characteristics, into all my properties, I have to say just the same thing. Generally, because I have to talk about the trend of my size, that is my size is decreasing. If my size is decreasing, I would talk about the configuration. Now this time I say that it decreased till chromium, because it is simple to remove the electron, the number of electrons that is increasing, and the size is bigger this time. At that time we used to say that when I am moving along a period, the value was something else, but that was a different case. This time, because I say simply there is the electron which is present, which is into my D shell, it is easy to extract that, right? Now if I have done that till my chromium, I have done this thing. Now when there comes the point that I have to take away an electron from my Mn, what happens? I know this thing that in case of manganese, what is that? That is nothing but my 3d5 4s2. Now S is completely filled, I have a configuration, I have a filled shell, right? And it is always very difficult to take away an electron from the filled shell. And apart from that, not just that, the D subshell is also half filled, which is adding on to its stability, right? And if I am adding on to the stability, what am I doing? I am doing nothing, but I am talking about more and more energy. If something is stable and I have to disturb it, I have to bring randomness into the system, of course I need to give the energy, right? That's what I have done. So now if I have to remove electron from a stable configuration as compared to the previous one, I need to give higher energy. Now of course it would keep on increasing till my iron, because I am getting a stable configuration, the addition of electrons, that is somewhere strengthening the bond. Then if I say, then when I am coming downwards and almost the same I observe. Now this is seen somewhere, of course the addition of electron is responsible, and apart from that I have to talk about the size as well, right? So that way, basically what my point is, what I am trying to say is that every time you have to discuss anything regarding your D block or the F block, you need to know the configurations. That's why I was saying just do the table again, even if you have not done it right, even now, go back, try to do it, write down just 3-4 times. If you would do that at least for 3-4 days, you would do the table, you would be able to talk about any of the properties, because the basic concept that is lying in my D and F blocks is almost the same, right? So this way I can discuss about my ionization enthalpy. Now one thing we would observe, that when I talk about the ionization enthalpy, this is happening when I am talking about the removal of just one electron. The trend that would see a different value, if I talk about my +2 oxidation state, of course that would be from my D1 to D10, that's what I'll get, because the 2 electrons, they have been removed. Now the easiest case for me, in this case, as I say that somewhere my Mn that has a high value, if I talk about the +2 oxidation state, if I talk about the transition elements when they come in another state, it is observed that the value would found to be the least. Why would it be? Because that is the particular tendency of each element to attain the stability. That's what I have been saying. Now if I am able to remove my 2 electrons, I would be able to give my Mn plus 5. That means D5 configuration. Same way to my copper, I would be able, as in case of my copper, I know when I am taking away 1 electron, that is giving me a stable configuration. That's why it is easier for me to remove it. That's why the value is low, right? But when I have to talk about the plus 2 state, now I know this thing because I have removed 1 electron from S. Now taking away an electron from the stable D10 configuration would be really tough. In that case, the values would seem to be reversed. Basically, the point is, what I am trying to say is, now I have just generalized this particular trend for a plus 1 oxidation state where I am removing just 1 electron, right? But I am saying that this was happening for this. You just need to see the configuration that you have. You just need to see the electrons which are into your outermost shell. Now after that, what we need to see is every time whether they say plus 2 oxidation state or a plus 3 or plus 4, you have to see that whether that particular oxidation state is leading it towards stability or not. And in case if it is leading it towards stability, the energy would be low. In case it would distort its stability, the energy would be high, right? So that way we can write down the trend for our ionization energy. Now coming up to the next trend, if I have to talk about your electrode potential. Now again an interesting graph is observed for the value of your electrode potential, and interesting thing is that you don't have to mess about the configurations, you don't have to worry about the size, you don't have to worry about all these things. The only thing that is going to matter in this case is because this is based on your thermodynamical activities. Now that is happening. Now if I say I have this particular trend, now this is what is happening. Again I am seeing I have taken up the value of your electrode potential. And this side I have your, of course, the transition elements, right? Now I observe that the value of your graph first showing an increase, then again leading to an increase somewhere like this. Now what do we see? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Basically this is starting from here. Here I have 3 elements. Then taking up 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. The circle that I have drawn, that is just representing the particular element where I am starting from a scandium and moving till my zinc, right? So if I write down scandium, and this would be my zinc. Now, what do I see? That again I observe an abrupt increase from my electrode potential. Now, the only reason, or not even the reason, you are not supposed to do that. What you have to do is, generally they would just need the graph from you. If you even know the trend, if you even know where it is increasing, where it is decreasing, you would be able to explain it pretty well, because you have to simply write that this is based on your thermodynamic calculations, apart from that based on the oxidizing and the reducing behavior. So we do not have to discuss much about it. And again, as I have been saying the same thing, that every trend, every property that you have to discuss into your D and F block elements, you have to talk about their configuration, and that's what you would be doing again. So electrode potential, as I know, that is nothing but the power that I have. I am comparing it with my standard potential value and I would lead to such a trend, right? So simply you have to talk about the trend. Another property, if I discuss with you, now if I say oxidation states, and I write down scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Now we will observe that the D and F block elements, that is my transition elements, they have the particular tendency to exhibit variable oxidation states. And variable oxidation state as in, of course for some of the cases there is not going to be much of the diversity, but there would be some cases where I would observe very high variation. So if I start with it, of course you know about your Mn. If I start with center, that Mn that goes from your +2 till your +7 oxidation state, right? Chromium that has a tendency to show 4 variable oxidation state, now this is 2, 3, 4, 5 and 6. Right. Now if I talk about these two, now this time first of all scandium that starts from your +3. Now these are the trend, they are going from your 2, 3, 4. Initially I would just observe an increase in the value, right? Scandium that exhibits only one oxidation state, and that is totally based on the fact that it has a small size and it can show the state, the maximum state which is exhibited is the total number of the electrons which are into its penultimate and anti-penultimate. That is my d orbital and my s. So it simply exhibits your +3. Then I see an increase, it goes from a 5, 4, 5, 6 and 7, right? Then there would be a decrease in the trend. Last one it would be +2. Here I would be seeing from +1, +2, +1 and +2. For cobalt and nickel, it would be 2, 3 and 4. 2, 3 and 4. And for the case of iron, the value would go from your +2 till +6, right? So what I have done is, I simply talk about the oxidation states which are available to me. What I have done is, I simply say that scandium, the first element and the last element, the stable state for them is the electrons into the outermost shell. Zinc it is +2, this is +3. Then I am seeing an increase. Now manganese is the one that would exhibit the maximum variation, that would exhibit an oxidation state where I have different possibilities, right? Then talking about the next one, these two they will have +2, 3 and 4, for copper 1 and 2, right? So this is all about the different types of oxidation states available. Of course, we are still left with many properties and that we will take up in the next class. Till then what you have to do is just go through the lecture, and as I have been saying it to you, I said in the previous class, again do the table, just practice it, okay? Till then, of course, take care of yourself and have a great day.